Hello guys, welcome to our today's tutorial. We're going to look at the topic which is called spectroscopy and electromagnetic radiation in pharmaceutical chemistry, second year pharmacy. Alright, so under this concept which is spectroscopy, we're going to look at three different components, which is IR spectroscopy or IR spectra, NMR spectra together with mass spectroscopy. So let's try to describe these three components in a brief way. Alright, so the one which is IR spectra, or we can say the infrared spectroscopy. So infrared spectroscopy, it is just a technique or an instrument which is used to identify a functional group present in a molecule. So when we are talking about IR spectra, just remember we are talking about the functional groups. So this one, it only deals with the functional groups. It helps us to identify the functional group that is present in a compound. Remember, this concept about the spectroscopy, it is for compound elucidation. On other way, we can say it is helping us to know or to identify or to write the structure of a compound. So IR spectra, it causes the atoms or the nuclear, we can say the atoms of within the molecule to vibrate because of the interaction of the infrared radiation together with the compound, or the molecular bonds of the compound will cause the atoms to vibrate at a specific wave number or at a specific frequency. We say functional group, they absorb or they vibrate at a specific wave numbers or frequencies. How? So let me just show you how this spectroscopy, or which is infrared spectroscopy, is. So this is how it is. So it starts from 4,000 to 400 per centimeter. You know, this per centimeter, it means these are the wave numbers. You know, a wave, it is measured in, wave is a lambda. So to find this one, it is the wave number is 1 over the wavelength. So now, when we're talking about this RIS spectroscopy, which help us to identify or know the functional group present in a molecule. So now, from about 1500 going to this direction, here we say these are fingerprints. These are fingerprints. Now, from 4000 to about 1500 here, we find that these here, that's where we are going to use in order for us to identify a specific functional group that is present in that particular molecule. So now, in this part, you find that the molecules or the atoms, as they will be vibrating, they'll be showing some peaks. They'll be showing some peaks. And those peaks, they are the one that will help, or those peaks, they are characterized by the specific functional group. And you can tell to say this peak and this wave number, it is characterized by this type of functional group. So now we need to know the wave numbers in between 4000 to 500, which is for the specific functional group. So let's try to look at them. IR values, or the wave numbers. I told you that in IR values, you're going to find the wave numbers, which are IR value in the IR spectroscopy. So now, let's try to look at the common ones, which we need to know by heart, because in an exam you may be asked and some or to know or identify this functional group when you are writing, or when you want to identify or writing the structure of the compound. So the first one is carbonyl group. Carbonyl group, it is common. We need to know this one because you may be asked. In short, here these are the things that you're going to be asked. Either carbonyl group, you can be asked about OH, CH stretch. We need to know those things by heart. So now, this carbonyl group, they will show a sharp and strong peak in the what? In this part of IR, which is 400 to 1000. So now, let me write aldehyde, ketone, acid, ester, because these things they contain carbonyl group, and they vibrate at a specific wave numbers in a range. Let me just write them. All right, so these are the compounds that contains carbonyl. Aldehyde, they are carbonyl containing compound, which vibrates at 1730 to 1740 per centimeter, which is wave number. So ketone, it is this structure which vibrates at 1705 to 1740 per centimeter. So we have also an acid. Acid contains a carbonyl containing compound, which is this one, 1730 to 1700. So these, they vibrate at a specific wavelength, or in a at a specific wave number in a range. So you need to know this range. You can also have this, which is an ester. Don't forget, an ester, it is like this. It is also a carbonyl containing compound. Then here it is like this. So here it vibrates at 1730 to 1750 in a range. So when we are done, we'll look at one or two questions so that we can be clear on this. So these are the ranges under IRS values or IRS spectroscopy. We need to know these things because you may be asked. So not only that, we need also to look at OH and also CH stretch. So under this one, what we need just to know is IR values on carbonyl containing compound. It is near 1700 per centimeter. So near 1700 per centimeter, we are talking about IR values of carbonyl containing compound. So let's try to look at OH, also the CH stretch. Yeah, so these are the IR values of OH. So OH, you know, it can be found in an acid, so it can be found in alcohol. So OH, it shows a broader, which is a broader peak, like like this in other way. So when you look at this, you need to know, like, talking about the OH. So OH of an acid, it vibrates at 3400 to 2400 per centimeter. Let's try to look at OH at OH of an alcohol. It vibrates at 3000. So here it is 3650 to 3600 per centimeter. Then CH stretch. So here it is CH stretch, which vibrates at 3095 to 3010. So it is in a range. So when you look at these, it means that you are done with the IR spectroscopy. We need just to know this. Now we need to look at some questions, how to answer them. Now let's try to see this the other component, which is NMR spectra. So NMR spectra is nucleus magnetic resonance. So here we're going to find that we have two types of NMR spectra, which is a carbon-13 and also a proton NMR. But specifically, we are looking at the proton NMR. So when the radiations of a compound comes in, you find that they will come in form of electrons. Then these protons will cause the atoms to start spinning, and because of the radiation of NMR, they are very strong enough to cause spinning or excitation of atoms. So under this one, we need to know about the chemical shift, also the splitting effect, and integration. So these are the three things we need to know under the NMR spectra. So let's try to look at these components which we need to know, or concepts of NMR. So we'll start with chemical shift. So this chemical shift is defined as a resonant frequency of an atom in a molecule, and it is expressed in ppm, which is parts per million. So you may be given the information under proton NMR, then they will give you like this to say maybe it is 1.1, like this. So just know that they're talking about the chemical shift. It is a resonant frequency of an atom in a molecule, and you need to know that they are expressed in parts per million. So we need to know how these are connected, how these they are we need to know how these are connected so that we can write a structure. So now let me just give you the common one, or the common values of chemical shift, which is for CH, or how they are connected. So let me just write. So now in a range of 0.2, in other books you find 0.3, in other books you find 0 to 2.5. In other books you're going to find that 0 to 3 any. So 0.2 to 2.5, you are talking about the CH. So here, which is here, it is CH. It can be CH3, CH. So here it can be CH3, CH2, CH, just like this. And specifically you can tell to say from 0.9, in between here, 0.2 to 2.5, 0.9, you're going to find CH3. Then here, which is 1.2, you're going to find CH2, like this. So from 0.2 to 2.5, it is CH. It can be CH3, CH2, or CH, just like that. Then from 2.5, or let me just say from 3 to 5, from 3 to 5, or okay, so here you can just say from 2.5 to 5, you are going to find that it is CH connected to the one which is more electronegative. So this X here represents the element which is more electronegative. So CH is connected to the one which is more electronegative. For example, we can have oxygen, like that. So to be specific, I'm going to say from 3.5, in between 2.5 and 5. So 3.5 to 4. Remember, they are in ppm. You're going to find this, which is CH3, like this. You get oxygen connected to CH3. Then from 4 to 4.5 ppm, you're going to find this, which is CH2. Oxygen connected to CH2. Remember, these are in ppm, which is parts per million. So we look at this. So from 8.5 to 10, you're going to find this, which is an aldehyde. From 8.5 to 10 is an aldehyde. Remember, 8.5 ppm, because we're talking about chemical shift. So here, let's try to look at from 10 to 12.5, you're going to find this, which is an acid. Then the last one which we can look is the last one is 6.9 to 9. So here we're going to have a benzene, or aromatic hydrogen. So more specific, you're going to have benzene at 7.25. 7.25. Here it is ppm, like that. Okay, so we have looked at the chemical shift, which is the resonant frequency of an atom in a molecule, which is expressed in ppm. We have looked at the common ones with their values. Now let's try to look at the splitting effect, and we try to answer some questions. So remember we have looked at IR spectra, IR values with these common ones. We've looked at the NMR, which we need to look at chemical shift, splitting effect, and integration. So now let me just lab this part so that I can have space. So looking at this, which is a splitting effect under NMR, you're going to find that we're talking, it's just the same as spine-spine coupling. We need to know how these functional group, which I've looked at in IR, we need to know how these CH, how they are connected, how they are coupled. All right, so now here we use N plus 1, which is N plus 1 rule, because they will show some signal peaks, and N plus 1 can be used to determine the multiplicity of these peaks. So N plus 1 rule, it helps us to know the number of hydrogen, the number of peaks that are there at that particular time in NMR. All right, so here, this N plus 1, N, it means the number of hydrogen of an adjacent molecule. Yeah. So N, it means the number of hydrogen of an adjacent molecule. For example, here when I say, so here when I say N plus 1, let me just say N plus 1, it means we are going to have the number of peaks. The number of peaks. Alright, so N plus 1, it will give us the number of peaks. Remember, N means the number of hydrogen of an adjacent molecule. So here we are going to have these terms which they use singlet. When they say singlet, we are talking about this singlet. It is 1, which is when you say N plus 1 is going to give us N plus 1 is going to give us singlet. So when you say singlet is 1. So when we say 1, it means that the number of hydrogen here is 0. So here we are talking about how they are connected or coupled. So we are going to say singlet, it means that it is connected to the molecule which doesn't have the number of which doesn't have any number of hydrogen, or which doesn't have hydrogen. So here it can be connected to C. It can also be connected to oxygen, the one which is more electronegative, because of singlet, which is N plus 1 is giving us a singlet which is 1. So remember, for us to have the number of hydrogen of an adjacent which is connected to, so here we're going to say N plus 1 is equal to 1. Then number of hydrogen of an adjacent which is connected to is 1 minus C. So here it comes to the other side, it will be 1, so here which is negative 1, so N is equal to 0. So the number of hydrogen is 0. So this, when I say singlet, it means this compound which is singlet can be connected to the molecule which doesn't have hydrogen. So example, it can be connected to carbon, which doesn't have hydrogen. It can be connected to oxygen, doesn't have hydrogen. So let's try to look at the other one, which is doublet. So doublet, it is connected to, so remember here when we're talking about, let me just show you, we're talking about singlet, it can be represented as, for example here, so it's just 1 like here, so this peak will be just showing 1. So we're talking about doublet. Doublet is connected to CH. What does it mean? You're going to use N plus 1 rule, which is number of peaks is 2. Then number of hydrogen in the adjacent or on the adjacent atom. So here you're going to have N is equal to 2 minus 1, which is 1. So here number of hydrogen is H, which is just 1 here. That's why I said it is connected to CH. So here the number of peaks, which is doublet, will be shown this way, like this. You see? So here this, yeah, so here it will be like this, like this. So number of peaks will be shown like this. So here doublet. So here let's try to look at this, which is triplet. Triplet, it means it is connected to, so here remember, for n plus 1 to give us 3, it means we're going to say 3 minus 1 to find the number of hydrogen on the adjacent atom. So you're going to have it is connected to CH2 like this, you get? So here it will be shown in this. So here like this, showing like these are 3, which is triplets like that. So let's try to look at the quartet and multiplet. So here, so quartet means 4, so it is connected to CH3. Why? Because we say n plus 1 is equal to, quartet means 4, so which means number of hydrogen on the adjacent atom, we're going to say number of hydrogen is equal to 4 minus 1, which is here we're going to have 3. That's why you are saying number of hydrogen here, 3 here. So here it can be shown in this as a quartet like this, like this. So here, so like this. So these are 4, like, which is quartet like that. So these are the peaks that can be shown to show that this is a quartet. Then let's try to look at the last one, which is multiplet. So here we say the peaks, when they are more than 5, we say a multiplet, which can be connected to aromatic hydrogen, a benzene like that, and so forth. All right, so we are done with the splitting effect, which is spine-spine coupling. Let's try to look at the integration. So when I'm talking about integration, so this integration is so integration can be defined as the area under the peak, and also it can be defined as it is also defined as the number of hydrogen. You may be given like this 3, which means that you're talking about the integration 3 as a number of hydrogen as a 3. Let's try to look at a quick example which we can apply all the concept that we have learned. All right, so this is the question that we have. So we have been given the molecular formula, which is C4H8O2, IR, which is we have been given the IR value, which is 1740 per centimeter. We also have this, which is a proton NMR spectra, which we have this triplet, quartet, singlet. We all have the information about NMR, which is triplet. You're talking about the splitting effect or spine-spine coupling. Quartet leads. Then here 1.1 with this symbol, you're talking about the chemical shift, which are in ppm. So we can be given, you can be given something like 1.1 ppm or just 1.1 with this symbol. Just know that you're talking about the chemical shift. Then here 3H, you're talking about the integration. Remember integration. So here integration is the area under the peak, or it is also defined as the number of hydrogen. So here talking about the integration. So now let's try to look at this. We want to know or to write the chemical or the molecular structure. So here what we want is just to draw or write the structure of this compound which we have here. So looking at that IR value that we have been given, remember from here 1740. So we need to know those IR values of those common ones that I just showed you. So here from 1740 to from 1740 here, remember we looked something at 1730 to 1750, which was an Easter, and an Easter, you remember that. So 1730 to 1740 is an Easter. Then here in between this one there is 1740. So here you can tell, say this is an Easter and it has got 2 hydrogen. So here we have identified that this is an Easter, but we are not fully to say this is an Easter. So let's try to look at this NMR spectra which we have here. Triplet. So when I'm talking about triplet, remember we're using n plus 1 to give us the to give us the signal which can be, or the peaks which can be triplet, quartet, or singlet. So when they say it is triplet, it means it is connected to what? You see, that atom which we have, it is connected to CH2, because we are saying, so here we can say triplet, which is 3. You see, triplet is 3, so it has got 3 peaks, which is n plus 1, it will give us 3. So here, n, what is this? It is 2, which means that it is connected to CH2. Now, we need also to know about this, which is 1.1 ppm. So this chemical shift, what can we tell about this thing? So we're talking about, we said from 0.2 to 2.5, it is CH, which can be CH3, CH2, or CH, like that. But looking at that, we have been given that it has got the number of hydrogen, which are 3 here. So here we're going to say the number of hydrogen are 3. So here you know that 1.1, or which is in between 0.2 to 2.5, is CH, which can be CH2, CH3, CH just. But here it is 3H, which is CH3, you get? So it is connected to what? So here I can just write connected to what? So here it is connected to, look at this triplet here. It is connected to what? To CH2, because of the triplet, which is the number of hydrogen which are on the adjacent carbon, they are 2. So 2 plus the n plus 1 there, which is 2 plus 1, it will give us the triplet, which is 3. So we go to the next one, which is a quartet. A quartet is, remember quartet is 4. So here, again from 2, here it is 2.3. So here we can say from 0.2 to 2.5, we are talking about CH, remember. So here we're going to say, since here we have been given the number of hydrogen, which is 2 hydrogen. So here, looking at the chemical shift, it can be CH. So here it will be CH2 connected to what? So looking at the quartet here, it is connected to what? When you say n plus 1, n plus 1 is equal to 4 here, quartet. So number of hydrogen on the adjacent carbon are 3. So here it is connected to 3, like that, you get? So then, because it is CH2, you remember this carbon, it can accommodate how many bonds? 4 bonds here, like that, you get? So here it is just CH2, which the other one already is connected to CH3. So now, so here it is CH2, like that. So here we can say it is not only connected to CH3, but it is also connected to, so here you can say it is also connected to this. Here, this ester which we have said, ester, it is like this. Then here O, then here R, you get? So here it is connected to the one which doesn't have number of hydrogen, but is connected to the one which is Z, which has the number of hydrogen, which has 3, to give us a quartet. Then the last one is a singlet. Singlet, it means it is connected to the one which doesn't have the number of hydrogen. So here it is connected to the carbon, or any atom which does not have hydrogen. So here we are going to say, because of this which is the 3H here, it is CH3, like this one, connected to what? Connected to O. How? So remember, we said, let me just change the color. We said something like, okay, so here I'm just going behind. Yeah, so we said something like from 3.5 to 4 ppm. Here it is this, you get, right? So like this. Remember that, which is from 4 to 4.5 ppm, it is CH2, like this one, connected like this, you see? So here is not a double bond, it's like this. Okay. So now, looking at this, here, it is 3.65. 3.65, it is in between 3.5 and 4, which is like this. So that's why here you will see that CH3 is connected to oxygen in that way. So let's try to write now the structure. Remember, triplet USA CH3 is connected to CH2 here. So I'm going to write here the structure now. CH3, okay, CH3 connected to CH2 like that, you see. Then this CH2 is connected to CH3 and this. So here already this CH2 is connected to this one, and also this is connected to, so here you can write like this one is connected to, okay, to this, which doesn't have the number of hydrogen like that. You see, then you just connect this now. Sorry, not like this. This, which is this one. From what we have is 3.65 ppm. So here you just connect C like this. You get? So this is our answer like that. So singlet is connected to the one that doesn't have the number of hydrogen. Then this one was triplet connected to this. Then this one was quartet connecting to this. Yeah, so and this is the functional group. So this is how you answer questions when it comes in that way. Thank you guys for watching this video. Remember to share. If you have any question, just inbox me, then we'll discuss.